Hello everyone. In this recording, we're going to finish going over sorting algorithms. Previously, I exposed you just to what they look like, but we're going to go into a little bit more detail about how they're implemented. We're going to talk about their runtime, and we're going to just actually do a couple examples by hand just to be more comfortable working with them. So let's go ahead and start with just a little bit of recap. So the context that we were working with is we were looking at searching algorithms previously, and we see two different scenarios where this one on the left is a linear search, and it worked for a unsorted list because it ended up iterating through the whole one. Now search 2 over here on the right, it actually used the property that L is sorted, and it was able to break out. Now, it did not actually take the running time. For both of these, they were linear running time because it's worst case scenario. When we talked about this, the worst case is that the element you're searching for, E, is not in the list, so you have to actually go ahead and search the whole list anyway. Now, we did also consider the best case scenario. The best case scenario is notated using big omega notation. So when we're looking at a searching algorithm, big omega is 1, and that is to say it's the first element in the list. So E, whether it's unsorted or whether it's sorted, is the first element in the list. Now, it would be nice if we can do better than linear, and we actually can. We looked at the scenario of a logarithmic running time, or big O of log of n, where log is base 2. That was a binary search. The only issue was that binary search relied on the assumption that our initial list had to be sorted. So just kind of thinking about, well, what if the list is not sorted? How much additional work will we need to go ahead and get it sorted? So that's what transitioned us to this conversation about sorting. All right, so how do you want to officially sort a list? And there are several ways to do so. When we watch this video right here, 15 sorted algorithms in 6 minutes, and if you feel free to peruse that and spend more time with it. But we're going to really focus on just 4. We're going to focus on BOGO sort, which is sometimes referred to as permutation sort or slow sort. We also are going to go ahead and spend a little bit of time with bubble sort, selection sort, and finally merge sort. So let's go ahead, and we already talked about this, but let's just review it for the sake of this video. And I want to go ahead and maybe add a little bit more just to talk about it. So what is the worst case scenario when sorting? Initially, we just said when the list is reversed. And actually, it still kind of also depends. So, or I should actually say it may vary depending on the algorithm. So this is something you're going to explore a little bit in the next project too, is like, what is truly the worst case? So of course, the list is reversed is going to be like the worst case in a certain sort that we go or look at in this lesson. So keep that in mind. Again, sometimes just that every single one being out of place may also be worse than it just being reversed, because you could even imagine, like in a list that was reversed, 2 is still in the correct spot. But again, big O, we're considering worst case and things like that, are usually something asymptotically much larger. So the best case is still pretty much always going to be the same regardless of what algorithm, and that is that it is already sorted. There's no more work needing to be done by the sorting part. But remember, to do a sort, you're still going to have to make sure that everything is in the right spot. So there's still a linear number of operations that need to be done. So of course that kind of puts a best case scenario on a sorting algorithm. So keep that in mind. Okay, BOGO sort is essentially just shuffle until we're correct. So we looked at that in terms of throwing up a bunch of cards and just playing 52 pickup. And this is a illustration of BOGO sort. So let's go ahead and look at that again. yeah, so here it is. Just as a reminder, if we watch any of this throughout the lesson, the sounds being played deal with how high or the largest value that we see right here. So it's basically just swapping elements and hoping that eventually all of the elements get right. Let's see, does this actually ever get right? So the, okay, cool, we have an ad, that's okay. We'll just go ahead and close that out. So at the end of that algorithm, it essentially sped up eventually to get that. So bogo sort is very slow. And in the next project, so let me go ahead and just pull that out just so we can maybe talk about that a little bit in the context of this lesson. So the next project, you're going to be doing an analysis, and I have a program or 4 programs here that each implement a different type of sort. And that is compiled, so you actually can't see the course code. This is the source code. This is like going to be a black box, so you're just going to see the results of the sorting on various inputs that you can go ahead and experiment with. Now, when you're doing bogo sort, of course, this would be a slow time or being slow. So if you ever feel like something's not going fast enough, or maybe you're doing a really slow sorting algorithm, let me just emphasize that you can always exit a program by just using a keyboard interrupt. Anyway, you'll experiment that more with this next project. So moving on with the lesson. There is a helper method or a helper function right here that just checks if the list is sorted. So the way this little helper function is working is if you have some list data, say it's like 1, 2, and 3, and then data 1 right here is going, this is using Python slicing notation, so it's essentially going to ignore the first element, so the data from 1 to the end is going to look something like this. And what it's doing when it comes to the inequality right here is essentially zipping these 2 lists together and then comparing and iterating through them together and comparing. So it's comparing that. If that is going to evaluate that as true or false, it'll evaluate that as true or false, and so on. And again, even the zip function right here is even dealing with this being empty. So feel free to play with that. But if these all evaluate to true, then all is basically going to say, are they all true? Then it'll return true. If it basically just does a big and on the whole list of booleans that were generated. So you can see right here, this is going to check if the data is sorted, and this is sorted is where we have the best case scenario. You only have to run that is sorted. Now the downside is you may have to run that is sorted a infinitely number of times if you're very unlucky. So that is the unbounded case. So that is bogo sort. If you're lucky, it's the best. If you're unlucky, it could take eternity. Anyway, there's bogo sort. Let's go ahead and look at bubble sort now. So to summarize bubble sort, you're going to repeatedly, let's go ahead and fix that grammar. You're going to repeatedly swap adjacent elements if they are in the wrong order. So let me go ahead and essentially paste over here the pseudocode. Pseudocode is basically just the algorithm without necessarily the syntax of the list. So you can see down here we have the syntax of the language, not the list, the syntax of the language. So this is how it's going to work. The pseudocode is we're going to write a program that will compare consecutive pairs. So you can see our actual implementation is doing that right there. And then it will go ahead and swap elements in such pair that so that the smaller is first. So you can see right here, it's going to just make sure it does a little bit of swapping. So that's this swap step down here. Actually, just this is the swapping right here. When we reach the end of the list, we're going to simply go ahead and start over, and we stop when there's no more swaps that are going to be made. So you can see that if we went ahead and got through the whole list and there were no swaps that had been made, then we'll just go ahead and not do any more times through this loop. So bubble sort was illustrated right here. And just to show you something a little bit different, this is linked in the project description. So in the project description, in the recommendations, I link to this visualgo.net. And it's, if you look at this, we have bubble sort right here. Now you could, of course, play with this and just run the sorting algorithm, and you could step through it slowly if you want. But you can see it's comparing, and it's always making sure that the smaller one is first in the pair. So we actually did a bunch of swaps there, so we're going to go back to the beginning and repeat. So you can see it's doing the same thing. But the reason this is called bubble sort is because the highest element just kind of bubbles to the top, or the largest value bubbles to the top. So you can watch here, 30, 46 is going to bubble its way to the top, and you'll find that after n steps, the last n elements are sorted. So now something that might be interesting to observe is what does the best case look like here. So just to see how this plays out, let me make this a little bit bigger. That should be better. I'm just if I could create the list. I'm going to make it sorted, but I'm going to, so I want it in increasing order. So if you think about what's going to happen, I would encourage you to pause the video and just think about this before I hit play. All right. Well, I hit play. I'm going to go ahead and do the sort. But notice as it goes through each pair, it doesn't actually ever do any sort of swap. So it only had to go through the list once. So that actually gives us our big omega running time on this. Let's go back to the notes. And worst case scenario is going to have to go through the whole list n times. So let's think about this. So while it's not swapped, it's going to have to go through the list n times. But each time it's going to go ahead and have to also do a linear amount of work. And again, we saw that just as it was going through. Let's go ahead and just look at this one more time. Let me just go ahead and randomly set this. And so the first time it goes through, and so there was a linear amount of work, and just to move that one right there, now it's essentially going to have less, it's still going to have less than n, but it's still going to just differ by some additive constant. So it's the nested loop is going to be smaller, but still in big O notation is going to drop the additive constant. So that is why bubble sort is worst case scenario, big O of n squared. Best case scenario, big omega of n, because you just have to do one pass through to verify that it's sorted. One thing I would encourage you to do just as you get ready for this next project is just actually go through and try and do the algorithm by hand a little bit. So you can see initially we set it to false because we're going to need to go at least one time through the list. And so we're going to say, okay, swap while not swap. So we're going to set swap to true. And again, if we ever encounter a scenario where we had to do a swap, we'll set this back to false. So we have to go back to the beginning of the list. So if we think about this, here's our initial list. And our first time, we're going to go from 1 to the length of n. So j is going to be 1. And we're going to look at this first pair. You can see that 4 is indeed going to be larger than 3, so we will swap that. And then remember, each iteration of j, you're just going to go ahead and bring everything else down. So we just did the one comparison. So you don't compare them all at once. If you're actually writing this algorithm step by step, you're just looking at 0 and 1. So j was 1, and we compared that with 0. So So again, this right here, if you think about when j is equal to 0, we were comparing these two elements. All right. But because we did a swap, now we're going to change that to false, and that means we just have to go through a second time. So next thing you're going to do is you're going to compare, let's do it here. So you're going to look at this list, and you see 4 does need to bubble here. So that means 3 comes down, 1 and 4, 1 and 4 are swapped, and 2 stays there. So that was the jth iteration. And the length of n. So here we have the length of 4. But remember, it's not inclusive, so we're only going to do 3. And you can see we compare these last two. So 2 and 4 swap, and then 3 and 1 come down. Now, since this was false, we're going to have to do another iteration. So let's go ahead and do that here. So this is the first iteration. We'll call that the first. We did 0th iteration. I don't know. You could call that 1 and 2 if you want. Doesn't matter. Just how you kind of start your counting. But okay, so we set this back to true, and let's go ahead and j goes back to 1. So we look again at these first two, and we see 3 is less than 1. So 1 goes here, 3 goes here, but that means we're also going to have to change our swap. I guess we call it swap above, so we could call this swap here just to match the actual Python code. And then 2 and 4 come down. All right, next step. You're going to compare these two right here because j is 2, so you compare the second and the previous element. So that's 2, 1 comes down, 2 goes here, 3 goes here, and 4 comes down. Now we aren't doing anything to break, so even though we see it sorted right here, we go ahead and hit 3. And so at this point, we compare these two. There's no swap that happens, so we do 1, 2, 3, 4. Oh, missed. So we got to be careful here, because really, the algorithm's not done. Because again, we set it back to true, and now we have to go through a third iteration where you do 1 to the whole length of the list. So you check these first two. There's no swap, so everything comes down, but that stays true. And the same logic happens every time as you go through that last iteration of the loop from j equal to 1 to the length of the list. And of course, remember that's range is one-sided, so that will be true and true. So I would definitely encourage you just to kind of play with bubble sort, be able to reproduce that logic by hand. In worst case, it's n squared, but it actually has a really good best case because it's just going, if it's already sorted, it's just linear. It just does the check. So let's go ahead and look at the next one. So selection sort. Selection sort repeatedly selects the minimum element from an unsorted part and puts it at the beginning. So if we just look at this, let's actually use the visual algorithm again. So I'm going to go ahead and do selection sort, and I'm going to just sort, and you can see the height of the bar is just going to be associated with a number. So it's going to iterate through, and it's going to just go ahead and look for the smallest element. So you see 8, sees 4, and then 4 is going to be swapped to the front of the list. So it's selecting the element that's supposed to go here, and it puts it there. So that's why it's called selection sort. Let's go ahead and just take a look at the scenarios where it was in kind of reverse order. So let's go ahead and look at it. So let's look at sorted, and let's see, it's non-decreasing. So if we sort this, we want to, so this is the best case scenario. The list is already sorted. So if we go ahead and sort this, but let's look at kind of how this approach. It's going to look 16. It has to check for a smaller one. It doesn't see that, so 16 stays where it's at. Then it's to do 22, and it's going to check to see if it sees something smaller, and it sees that's where it's at. So the downside here is that it is still going through the list n squared time, or is doing n squared steps to go ahead and verify that the list was actually already sorted. So that's a little bit of a downside. In the best case scenario, it's still doing a lot of work. So the way you implement this here in Python is as follows. Is just for simplicity, I just said n is the length of the list, whatever the input is. And here's the outer loop. So you're going to iterate through the list. And remember that it's going to move the smallest element to the front. So if you think about like the first time through, like when I is equal to 0, j is going to still have to go from 0 all the way up to n. But the second time through, when I is 1, j already, you don't need to hit j equal to 1 or 0 because you already know that that first element is in the correct spot. As a side note, this is a little bit of Python syntax for reassignment. So this one essentially is going to take, this is a quick way to do swapping in Python. Python has this kind of like syntactic flair that it knows how to handle the swapping. So you can see the minimum value is stored, or the min index, wherever that was is going to be put to wherever ith is. So that's the one you're trying to select and put in the right spot. And then you're going to move whatever was in the wrong index. You'll just move it to wherever. You'll just do a swap. In a lot of languages, it's not smart enough to do that because it doesn't know the order. So that's why we did up here. It basically stores it in a temporary variable, updates, and then it does the swap. So that's again how you would have to do it in like C or Java or a language that isn't maybe have some of these nice modern syntaxes like multiple reassignment. But okay, so let's see what that means for the running time. So worst case scenario is going to go ahead and you can just see this is like big O of n. And then this again is, this is smaller, but so it's going to be like n minus some constant c, but again, it's going to just collapse to the dominant term, which is the linear term and not the constant. And nested loop, you have the actual squaring or the multiplication, so that's big N of n squared. And unfortunately, even in best case, it was also big N of n squared. There's nothing here to shortcut out earlier. So not a very efficient algorithm, but it's a fairly intuitive one to understand. So let's go ahead and you could watch this video right here if you want to see how to work out by hand, but you could double click here to draw. So let me zoom in and we'll just kind of save the drawing here. There it is. Okay, so what we'll do is we're going to have 2, then 8, then 5, then 3, then 9, then 4, then 1. So let's look at 2, and you're going to just kind of search along until you find something smaller than 2. Oh, okay, we found something is smaller than 2, so you're going to swap them. So 1 is going to go, so 1 will go here. I'm going to underline that because you know that's now sorted. The 2 is going to go over here, and you could even see like the part of the inefficiency is it would have been nice if we could have put 2 like right there, but it's just going to swap. So 8, 5, 3, 9, 4, and come down, and the 2 we already swapped. All right, so now you're going to look at select the correct element here for 8. So okay, you would kind of store 5 if you were doing the algorithm, but if we're doing this by manual, we're just going to find that, oh, 2 is what's supposed to go here. So 1 will come down, that's sorted. 2 and 8 will be swapped, and then we'll go ahead and have 5, 3, 9, and 4. So 1 and 2 are in the correct spot. Then we repeat. You can see that 3 is supposed to go here. So 1, 3, 1, 2, 3. And those are sorted. And then 5 was swapped, then 9, then 4, then 8. Then your look 5, that needs to be 4 there. So those are a swap. 1, 2, 3, 4. 5 ends up over here. 9 comes down and 8 comes down. So these first 4 elements are sorted. All right. Then we will look at swapping 9 and 5. So 1, 2, 3. Ooh, that was a sloppy 2. So 2, 3, 4, 5. And 9 is there. And 8 comes down. So these are sorted. Then we do 9. That needs to swap. 1, 2, 3, 4, 5, 8, 8, 9. And then you can see those are sorted. And then, of course, the last one is be like, oh, okay, that is sorted in the right spot. So anyway, that's how to kind of work through that one by hand. I would encourage you to maybe play around, like what would it look like if the list is reversed, just to get a feel for how selection sort works. All right, so there's selection sort. Now, the last one, merge sort, is a divide and conquer algorithm that divides the input into 2 halves. It calls itself for the 2 halves and then merges the 2 sorted halves. So what that means is we're going to do some sort of, calls itself. So that means that this is going to actually be a recursive function. And then you can see that here in the pseudocode. So this is actually a pretty good implementation of merge sort because it's relying on left and right indices instead of actually doing any sort of copying. So it's actually pretty good that way. So if the right is is greater than the left, so again, that's essentially making sure that your indices are correct. If they're the same, then you have a list of just length 1, and you basically will not do the merge sort, and you'll see that as we write through an example by hand. So what we're going to do is find the middle point. So the middle is just going to be the left plus the right minus 1 divided by 2. So it looks like this is just accounting for different indexing. So I feel like we do need to definitely add some order of operations there. And then what you'll do is you're going to call the merge sort on the left half and then on the right half. And then what you'll go ahead and do is once you're going to basically go into the call stack with a smaller list until you essentially get down to a list of just size 1. And then you're going to merge them. So let's actually do this by example before we go into the pseudocode. So if we let's go ahead and just take this example right here that we're provided, paste that in just to make it a little bit easier. Okay, so zoom in a little bit. So zoom 200. All right. So the way this algorithm is going to work is you start with your initial list and you're going to find the middle. So let's see here. What we'll do is we'll take the middle up to 3 because it wasn't necessarily doesn't divide evenly. We'll take the 4 and we'll put the left side over there, and then we'll have the right side over here. So what you'll end up with is you'll end up with 2 arrays. So you're going to call merge sort again using 38, 20, 27, 43, and 3. So that's going to be the left array. And then you'll also have the right array. So that's 3. A little sloppy here. Sorry about that. And then you'll have 9. We'll go with that. And then you'll have 82. And then you'll have 10. Okay. So now what you'll do is technically, if we were kind of following the order, these right here, I need to go ahead and move this over a little bit so I have room to write. I'm going to need to scroll. So let's slide that over here. Good. So what you'll then look at doing, let's get scribble, there we go, is you're going to, again, split this one in half. So that's going to go to the left. Then you'll have the other side over here going to the right. So you'll have 38, and then you'll have 27. So you have an array here. And then you have 43. And then you'll have 3. And then the same logic happens over here. Technically, you would actually just going down the call stack, you would technically be doing this one next. So let's kind of match that. So you would really not have even done this over here left because as you go down, you're going to keep calling. So then you'll end up, you'll have the middle, which is going to be 38 on the left array, and then you'll have 27 on the right. And then you can see you're not going to do another recursive call here because this one has a length 1. So the left and right index will be the same, which means then you'll go ahead and let's just make that a little bit cleaner. So this is 3. So that means, like, okay, you're going to go back up to here. Then you're going to take the left array, and that's going to be 43. And then you'll have 3 over here. So now what you're going to do, it's not going to do any more recursive calls because the left and the right index are the same. So what it's going to do, it's going to start merging these. So it's going to merge these, but it's going to do that in order. So what's going to happen is 27 is going to be put first. So it's merging this now into one list. So 27 will be first, and then 38. So it's merged those two. And it's to do that same logic over here. It's going to merge these two, and it will end up putting 3 first and then 43. Okay, and now it's still merging, so it needs to merge these two arrays. So what it's going to do, so this is one array, this is another one, and it's gonna, as it merges it, it's going to do it in a way that's going to just grab the smallest element. So it's going to merge into one array of size 4. So 3 will go first, that's taken care of. Then we have 20, so it's going to look between, is 43 smaller than 27? These are sorted, so it doesn't need to check all of these, it just needs to check the first one, and that's kind of the power of this. So that means the 27 will go next. And let's slide that over. Okay, and then the fourth element in the array, again, it's already looked at 27, and again, it just is going to look and compare these two. Sees 38, so let's go ahead and put 38 here, and then lastly, it's going to do 43, so that's merged. So if we zoom out here a little bit, we should be able to see kind of what's happening in terms of the tree. And what will happen next is so you can see it's splitting, and then it's splitting again, and then it's merging, hence it's called merge search. So what I would encourage you to do is try and go through that logic through the right-hand side, and then ultimately you're going to end up merging with whatever you get there with a list of size, I think this was 7. So 1, 2, 3, 4, 5, 6, 7. So I'd encourage you to try this, pause the video. All right, so let me go ahead and put up the answer, and just to make it a little bit cleaner, I'm going to just grab the one that was already nicely formatted. But you can see right here, we have the splitting of the arrays down to a single element, and then we merge them. And it'll get, a lot of the power of this comes from, when we're merging, we don't have to look at the whole list. We know that these are already sorted, so we'll just look at this one and this one, grab 3. So that's done. Then we would look at 27 and 43, grab 27. Then we'd look at 38 and 23, grab 38, and then 43. So it's really nice because what happens is the process of sorting, again, when you sort a list of just 2, that's easy. You just put them there, and it's we've reduced the problem size. So here's the Python's implementation. You can see here's the merging process. I would encourage you to spend some time and look through this logic right here. So this first logical block is essentially just going through and is just grabbing it or is grabbing the smaller one. So if the left at I is less than the right one at J, and again, left and right are actually lists. So keep that in mind, we're indexing to it. And then you have some result, and it's just going to, if it grabbed the left one, that means that it's going to append that, and it'll now be looking at the next one in the left list. And then the same thing could be happening if the right list was larger. So if we look at like right here, when we were merging these, when we were doing the, you put the 3 in, the 20, so it saw the 3 was larger, so we iterated to the j equal 1 in the right list first. So just kind of trace through the logic here. And then, of course, you might have a scenario that you run out of like left and right, or one of them first. So this is just like when the right list is already all been added, you're just going to go ahead and append the rest of the left one on, and so on. So here's the merging. It's pretty, the most of the effort right here is in this merge step. So the merge sort, again, I think the pseudocode was slightly different, where it was like left is left than right. This is just saying if we end up with or with the left index is less than or if the right and the left index match. This one's a little bit different. It's just saying if you get a length less of length less than size 2, then just go ahead and return. And this says return a copy of it, because you'll want to keep in mind that list pass by reference. So you actually should be passing in copies, which is what we're doing with kind of this this right here. All right, so it is the merge is big O of n. That's, like I said, a lot of the work. The merge sort is log of n, because we're dividing the problem in half each time we call this function. So we call it here with the right-hand side, or 0 to the middle. So with the left-hand side, and then from the middle to the end. So and again, we're not messing around with like the +1 or things on this one, because Python slicing does not include the right endpoint of a interval. So then you eventually are just going to merge. And okay, what's that mean? So if you look at this, every time you call merge sort, you're going to do log of n work, but you're going to have to also do this. So like this is like 2 log of n, so there's log n, but then you're going to also have this to do right here. And that's going to happen in each side of each one of these. So that's actually going to make this a product, because this is nesting. This is happening inside each one of these as well. So worst case scenario, it is big O of n log n. And the reason being, so let me just copy and paste that over here, because each of the big O of n log n recursive calls has big O of n work. And again, it's kind of nested in there doing this merge, so that is where we have this. Now, best case scenario, even if it's sorted, it has to go through all of these. So let's just go ahead and actually look at what it looks like when it's sorted. So let's go to merge. Let's go ahead and create a sorted one, and let's watch what happens. So you can see right there, it's still having to, let's see how the color coding is working. Okay, so red means it's sorted. So you can see right there, I'll slow that down a little bit. Okay, let's step through it. Okay, I see. So there's the merging. So, okay, size 1, and now it's going to merge those. This again merge because they're all in the right order, and then this is the red and the yellow are now being merged, so they're merged now. Okay, and it's going to go through a similar thing over here on the right. So you can see it still needs to, even in the best case scenario, it's going to go through and basically get down to a list of length 1 and then do the merging. I think it was a little bit easier to see when it wasn't as colorful for once. So you can always look at the merge sort YouTube video right there, where you can more explicitly see what is sorted where, and I'll leave that for you to watch again if you would like. So let's summarize. Oh, by the way, let's add a reason right here. So best case scenario, big omega is still going to be big n log n. And the reason is because all of the work will be done regardless of whether it is already sorted. All right, so let's summarize all of this. So here's a little chart that summarizes that I think it'll really help you in this next project, because the next project, what you're going to go ahead and do is you're going to analyze the running time for these 4 different sorts, and these 4 different sorts are going to be one of the 4 algorithms that we went through. So you want to kind of play with it with different sizes of lists, whether they're reversed or sorted or shuffled, and you'll go ahead and try to argue by doing with a stopwatch. And I tell you how to do that in the project description. But here we go. BOGO sort, worst case is unbounded. Best case is linear. Bubble sort, worst case, it is going to be big O of n squared, because everything's going to have to eventually bubble to the top. So worst case scenario, everything, like if the list is reversed, you're going to have to bubble everything to the top. Best case is already sorted, and you realize that first time through, so is big omega of n. Selection sort is best case and worst case is big O of n squared, and merge sort, best case and worst case is n log n. Now, one other thing I want to maybe throw out there is just keep in mind that n log n is actually better than n squared, which is just n times n. So if you look at it that way, you're just comparing log n and n, and of course, like if you divided those out, you can clearly see that merge sort is really kind of the best algorithm we have here in the case of worst scenario, but these two definitely do better if the list is already sorted. So that's just something to keep in mind. All right. So with that, it completes the discussion on sorting algorithms. Spend some time. My recommendations are look through the pseudocode, step through it yourself. Go ahead and actually do some of these problems by hand, just so you get a feel for what the sorting algorithm's doing. So get a piece of paper, and I know that's weird in a computing class, but get a piece of paper out and do that. And just think carefully about the different running times and how the construction or initial list affects that. And that's what you're going to be doing in Project 5. All right. If you have questions, feel free to reach out, but good luck.